All right, the first unit of the Intermediate Six Sigma Greenbelt course. Process data and documentation is a set of interrelated resources and activities which transform inputs into outputs with the objective of adding value. And we spent a great deal of time talking about value previously. If it's an important activity, document and control of it. What we're ultimately looking for is a systematic process, one that's repeatable and one that's measurable. If you can get that, then you can start controlling your process. With the thought being that if you have a good process, automatically a high quality product or service will come out at the end. There are different ways of modeling a process. The graphical ones are the best ones. So you can get a flowchart process map and ultimately a value stream map. Oh man, that you're there, because we are visual animals. Written procedures and work instruction, we can read it, but they're not easy to follow by the average person. The advantage of the value stream map, I'm going to spend some time with that, or just talk about it a bit, is it kind of combines process maps, but what it includes is a lot of data: cycle time, inventory, tack time, everything you need to know about how that value goes through that one little step in each one little step of the value stream map. When I first heard of this thing called the SIPOC, supplier input, process, outputs, customers, I said, yeah, of course, duh. But you'd be surprised how many people can't identify the input. It's more than just saying this comes in. How does it vary, the input? How does the output vary? And how do you document the relationship? And this feedback loop that you get from the downstream metric, you take that information that you get from downstream, the next step or next few steps, all the steps beyond that, and go back and say, how does the supplier influence my output? How does the supplier affect my customer satisfaction? And you use that to get better, to improve. This is a modeling of how to prepare tea. It came from a British source, and I didn't have the imagination to come up with a better one. So pretend like you're British, and this is how you make tea. And just take a look at it, see if it makes sense. And if you were making sense of this, if you look at the customer, whoever you're serving the tea or the housemaid, you would get for some input from them. What do you think of this cup of tea? And then you use that information to see, ultimately go up to the supplier. What about the grocery store? Who's making it? The kitchen cabinet? Does it make a difference where I store it? And there's the input. Can I change some input? And see what that effect has on the customer ultimately. And there's your feedback mechanism. The customer ultimately feeds back through every step of that SIPOC. Temperature boil. There's some people said, do you put milk in first, or do you put milk in after you make the tea? I don't know. In the reading, I'm going to talk about the rational matrices, that cause and effect matrices, and cause and effect fishbone matrix. That's also, I'm going to focus on the second bullet here. That's the Ishikawa diagram. If you go to asq.org, there's a free template you can use. But basically, they say there's 6 variables that influence the output, and all you try to do is brainstorm. And once you brainstorm that, you say, what will affect the output the most? What's causing this problem? And then you work on it, and you improve, and you get better. Great tool, very visual. It gets everybody involved. The fishbone diagram. There are different ways, different types of data, and depending on the data type, it depends on, it'll affect how we analyze it. First thing I like to talk about is attribute, and I'm going to use my car as an example. It's discrete. I'm going to talk about how many defects there are on my car. Well, it's got a cracked windshield, the door handle's broken a little bit, it's the radio doesn't, there's a speaker on the radio that doesn't work. Just all kinds of, so I got 3 defects. I can't have half a defect. It's either there or not. Okay. And another way I can do it is I got a defective car. It's either good or bad. Well, it's a little bit broken. It can't be half broken or not broken. It's either broken or not broken. That's attribute data. Variable data is continuous data. In other words, how much does my car weigh? Well, it's a couple thousand pounds. No, it's 2,130 pounds. Or you can keep on breaking it down. 2,130.6345. You can go on forever. That's variable data. How long? Money's a variable data. Time's a variable data. In other words, you can keep on breaking it down into finer and finer elements. The last one is locational. Where did it happen? I've seen these also called measles diagrams. I've seen this used quite effectively in analysis of accidents and safety. Where did somebody fall down? Where did somebody get hurt in the factory? You put a little pin where it happened, and you can analyze where it happened. You can say, okay, this is where most of the accidents happen. What's special about that? And see if that happens. That's locational data. Again, building on my car example, okay, there's some continuous data and attribute data. Just take a look at this and see if it makes sense. Okay, this is the crux of Six Sigma, collecting the data. First of all, you got to figure out what your problem is, the define stage, and then you got to find out what measurements, what metrics will tell me most about this problem, and then you got to figure out how you're going to measure that thing. So you got the technique. You collect the data, and then you analyze it, and we'll talk about that later units. But collecting data, you got to have data. And again, it's all about measurement by facts. You got to get the facts, and that's data. So how do you collect and summarize data? ASQ, again, has check sheets and checklist forms collected. If you can, take the operator out of it. Every time I ask the operator, I'll take a part out and give them a ruler or something. Say, how wide is this bracket? First question out of their mouth is, what's it supposed to be? And you'd be surprised at how many times they get exactly what it's supposed to be. They have that bias, that little fudging. But again, if you can take the operator out of it, great. And you'll be surprised how many times the data accuracy isn't that accurate. There's always that emotional bias, right? I want to look good. I had one operator, he'd sort through about 20 parts to give me the one that was best one, because he wanted to look good. Avoid rounding. The more detail you can get, the better. Record in sequence. What you want to do is you want to look for trends, right? Things change over time. If you don't do that, you lose that temporal element. And as soon as you see a change, you should be able to spot it. And you'll see this in SPC later on. Apply the statistics, the crunch and the numbers. You can screen or filter data. What data do you want to get? Avoid removal by hunch. And again, if you can spot an outlier, one that doesn't fit with the rest of the group, and it's obvious, those are the easy ones to fix, because they can usually be explained by some little tweaking or some little change in the process. And again, if you can include the time, the temporal, the machine, the auditor, the operator, gauge, lab, whatever you can do, because later on you can divide the data by who collected what machine made what. You can look for those differences, and you can do the statistical test and see if the differences are real or just random. One of the biggest problems I find whenever I do classes or work with industry, they chase a false lead. They chase in random variation. And you want to avoid that. You want to make sure you're barking up the right tree. Different types of sampling. There's random sampling. That's when you got a bunch of stuff. You pull parts out at random. In other words, everything in that group of whatever you're looking at, that whole population, has an equal chance of being selected and examined. That's a random variation. No sorting or anything. It's just, if you want to read an interesting study, look at how George Gallup got his start when he was sampling, doing polling for the presidential elections in the 1930s. Then there's sequential. This is where you got a continuous process, and then you keep on spinning it out, or service, whatever it is, and you just keep on pulling at intervals, certain intervals, right? Stratified, if you got like 2 suppliers, 2 batches, 2 whatever. This is used a lot in the food industry when you're getting, your supplies, like, pigs, for example. If you get pigs from 2 different farms, you can look at the differences. Anytime you got 2 different groups. This is stratified sampling. These are different graphical methods. Again, we're very, very, very much a visual animal. So box and whisker plots, I don't see much of those. Stem and leaf, not much of those. Scatter diagrams are huge. This is one of the 7 basic quality tools. Excel actually has a nice little graphing program. ASQ.org will have some of this, and you can get multiple free scatter diagram creators on the internet. Pattern and trend analysis. This is where you actually look for what's happening with the data as you go through time. Trends that involves time. Histogram, again, look at ASQ. I've got some in the reading. Excel will create that. Again, you get all these free. Normal probability plots. We're going to talk about the norm disk and all that in later chapters. But what are the odds of this just being random variation, or is it a real variation? Again, take a look at that. Look at the readings. If you have any questions, put it in the discussions. I wanted to show you a little bit about what a normal probability plot looks like, some of the key characteristics. What you got is you got the mode, the mean, and the median. They're all at the same point. You see 50% about greater than the mean, 50% less than the mean. And it looks kind of like it's very well balanced, right? And it's symmetrical. This is what a normal plot looks like. And this is the way things actually look like in real life. When Gauss first looked at this, he said, say for instance, I was looking at apples, and the average apple weighed about, I don't know, 72 grams. Well, half the apples that he pick out at random will be greater than 72, half will be less than 72. But that distribution, the further away I get from the average, the less and less I see. So I'll find very few apples at 95 grams, very few apples at 45, because I'm further away from the mean. I can find plenty about 72, 73, 71 grams, right? That's the way things are distributed. But theoretically, all things are possible. The area under this curve is 1.00 in decimal form, or 100%. And that's key when we start getting into probability.